recording is starting. So last time we looked at extending Maxwell's equations from static fields to time-dependent fields. Okay? And in particular, we introduced two things. One is, of course, Faraday's law that everybody should have seen before. And the other one is the so-called displacement current. So today we want to start with these two concepts. We're going to build upon it, and we're going to take a look at some of the the hunch that we developed last time, that something must be propagating in terms of electromagnetic waves, and we're going to actually take a look today exactly how that comes about from these equations. So let's start with a quick recap of what we've done so far. So, in particular, we looked at Faraday's law. And Faraday's law is basically saying that the electromotive force, EMF, is due to the rate of change of the magnetic flux. So in particular, this curly E, EMF, is equal to the negative of the rate of change, so the derivative of the flux of the magnetic field. Flux of the magnetic field, where this E, the electromotive force, which again last time we discussed this, which is not really a force, it's more a work done per unit charge. So this E given by the integral of the electric field over some loop, whereas the magnetic flux is given by the integral of the magnetic field across some surface. Okay, so this is exactly that we very early on in the lecture course discussed, is how many field lines cross a particular piece of surface. And if we put these two things together, we can use Stokes' theorem to turn this into a curl over a surface, and then we can relate this to the derivative of the magnetic field. Out comes rolling is that the curl of E equals to the partial derivative of the magnetic field. So this Faraday's law is essentially saying that with a time varying magnetic field, we get an electric field. In particular, we get a curl of an electric field. So before, the electric field was simply a field with just a divergence. So if we look at some static charge density, that only had a divergence. And now we're actually introducing a curl component, a rotating component to the electric field, but that is sourced by a change in magnetic field. So that's the first concept and the first step towards developing Maxwell's equations in a time-dependent sense. The second thing that we discussed is actually a concept that was introduced by Maxwell, which is the so-called displacement current. And the displacement current in this particular case is given by J underscore D, just epsilon naught partial E partial T. Okay? This is a, let's say a hypothetical current associated with a change in the electric field. And this term here basically does two things. Right? It basically restores the symmetry to Maxwell's equations. Because before, what we had is that a changing magnetic field is a source of an electric field. But then, the problem comes if you only leave it at that, then you don't have the opposite, where the change in the electric field comes to a magnetic field. And so by introducing the so-called displacement current, which is a current, or well, it's a hypothetical current due to the change in electric field. And this is something that was postulated by Maxwell. What it also does is it actually ensures conservation of charge. And in particular, it restores within Maxwell's equation the notion that the divergence of the current density is related to the change of the charge density in the following form. Okay. And again, recall the numerical notion of the divergence of the current, which is basically stating that there's a differential between what comes in to a particularly closed surface and then what goes out. Right? That's the divergence. And that should equal to the amount of charge density that flows out over the surface over a particular time. And so that's where this is. And so last time we showed that by putting in this displacement current of this particular form, we also restore this concept of conservation of charge within Maxwell's equations. And again here, the resulting equation is that the curl of B is now mu naught J, which is the current, the free current, and also the displacement current JD. It states that it's mu naught J plus mu naught epsilon naught partial E partial T. Okay, so when we look at the time-dependent fields, end up needing two things. End up needing the concept of a displacement current and Faraday's law, which then link the change in magnetic field to the electric field and the change in the electric field to the magnetic field. And so we finally arrive at the full set of Maxwell's equations. So Maxwell's equations, time varying fields, which are now given by the following. Okay, the divergence of E remains the same, which is just rho over epsilon naught. Similarly, the divergence of B remains the same, and then the curl of E, time derivative of B, and the curl of B equals mu naught J plus mu naught epsilon naught partial E partial T. Okay, so this is basically where we stood last time around, right? So we've got Maxwell's equations in time varying fields, and this is all well nice and well, but do we really have any experimental evidence for this? Last time I merely stated that there is, of course, experimental evidence for Faraday's law, and we can take a little bit of a closer look today at how one may be able to test it. Actually, this is very well documented and well tested. So one way to do it, for example, is actually using the magnetic field to generate a you can generate a a square wave of current. So one example would be, for example, if I have a magnetic field here. So there's some magnetic field confined within this blue surface, and it's coming out of the page. And what I'm going to do is I'm actually going to have a semicircle. So let's have a semicircle here of, let's see, I can draw this in a good way. Semicircle. Please don't laugh at my drawing skills. Opa. That's not too bad. That's not too bad. This is much better than I expected. So imagine we've got a semicircle here, a wire, okay, conducting wire, copper wire, whatever you want it to be, and we put this in some partially in some magnetic field, and so here we set this spinning with some angular velocity omega. So this here is simply omega t, this angle. And then, just for convenience, we can make this distance here a. And then we may ask, okay, well, what is the result in this setup? I'm setting this thing to spin. Right, why don't I think this is a good moment to at least give you a minute or two to think about this setup, how you would arrive at, the current that is actually being driven through semicircle wire, and we'll come back to discuss this in a moment. Okay, I'll give you 2 minutes. Okay, so hopefully you've taken a chance to, to look at this, and we can first qualitatively look at the scenario. Here, what we have is, we have a change. Okay, we rotate this circuit, we rotate it through the magnetic field, and so this wire here, this closed loop, will will have its flux change. That's step number one, right? The flux change. And so we can take a look at the flux. Here, the flux simply magnetic field over some surface. And then here we can actually take a precise look at, okay, well, what is the intersection of the surface? Because the field is uniform. Okay, well, in this case, because B and A are perpendicular to each other, so we can scale out this B, and so here what we're looking at is, basically the area. How does the area vary with respect to well, how does the area inside this magnetic field? This is simply given by A omega t A squared over 2. Of course, this is between 0, so omega t is 0, between 0 to pi. If we assume that when omega is 0, it is completely outside of this this ring. Sorry, ring is completely outside of this field. You can see if when omega t equals pi, but it entirely flipped, and so the entire surface is within the magnetic field. And similarly, we can look at pi. When it's not between 0 and pi, but between pi and 2 pi, well, again, we can then write that this is b times 2 pi minus omega t a squared over 2. Okay, so this is the other half of the cycle. So here the surface is decreasing, and this is after pi. After pi, so this is pi omega t 2. Okay. And so we know from Faraday's law before, from Faraday's law, we know that the EMF, the electromotive force, is just minus d phi dt. So here, what we have is something that is proportional to b a squared omega over 2. And of course, here the sign, so let me put plus minus, the sign depends on whether it is between 0 and pi, or whether it's between pi and 2 pi. And so if I assume that this circuit has some resistance R, then I just over R. And so indeed, if I plot this out, I get something that looks like this. This is I, then I get something that looks like a square wave. This changes negative I, 0. This is negative I0 up like this, and this, and this. Okay. So here we've take a look at the amount of current going through here, and we can see, okay, well, this is a square wave generated. So in pi, it suddenly flips the sign, and then in 2 pi, it flips the sign again, and so on. Otherwise, it generates a steady current. So this is one way in which you could experimentally test Faraday's laws. Okay, this is a good moment to take a quick break. Okay, 5-minute break, and what I want to do next is discuss things in terms of the other part, displacement current, and in particular, kind of the quest for the search for this displacement current and how it actually ended up, how we ended up getting the experiments that then showed the existence of electromagnetic waves. We'll do that after a quick break. So why don't we come back at 3 o'clock? Okay, and then we'll continue. Guys in a bit. Okay, it's 3 o'clock. Let's get back into it. So the next thing that I want to discuss with all of you is this notion of uh, the, or at least working towards an understanding of these electromagnetic waves. And so last time around, what we did see was the following. When we talked about Faraday's laws, assuming that we have some magnetic field here, then what we expected to see is some electric field. This electric field going like this. Then, of course, would we expect a symmetric situation when this field itself would be the source of a magnetic field. So, would we have a situation where we have a magnetic field going around this? Where there's a B field being introduced. And so this is, say that this is an expectation, right? Especially if you look at in terms of symmetry, and also when you look at, reduction of the displacement current is needed to have conservation of charge in Maxwell's equation. So what we want to do is we want to see if if you have a B field, a changing B field, which then leads to a changing E field, which leads to a changing B field, and so on and so on. So do we see this propagation of the electric magnetic field? So that's going to be, or that was the central question to the Hertz experiments. So the Hertz experiments were a series of experiments where in this case Hertz, a German scientist, basically set out to confirm one of these key insights. In particular, Hertz was set out to show whether the displacement current behaves like an actual current. Right? This was nowhere near a done deal. This was something theoretically that Maxwell had put into the equations because he wanted. Well, historically, Maxwell did it for very I wouldn't say bizarre reasons, but he had a sort of an interesting view of how these currents and how these things around, really in terms of um, mechanical cogs and rings that rotate and vortices and so on. But that is the historical part. But still, it is an important question to ask: is this displacement current actually giving you the same physical phenomena as an actual current? And in order to show this, or in order to at least test this hypothesis, Hertz actually devised a series of experiments which ultimately led to the confirmation of electromagnetic waves. So let's see what he actually did. Okay. So amongst his first experiment, and really the one that is set out to show that this displacement current behaves as an actual current, is the following experiment. So imagine that he has and I'm not going to go too much into detail, but let's assume that there's this box over here, which is able to generate let's call this R, and in particular R is able to produce high frequency oscillating voltage. Okay. And what we're going to do is we're going to then hook this up to two plates. Call this P and P prime, two plates. And in between this plate, I'm going to put some dielectric D, like this. Okay, so indeed, what we're going to do is we're going to put some voltage. So now we have voltage across the right over dielectric D. Okay, so what? Oh, okay. So first, what the question is, what do we, in this situation, what is it really that what we're doing, right? R is producing a high frequency oscillating voltage, and so in between plates P and P prime. So what happens here is that what we're basically producing is a changing electric field in this dielectric. Okay? And so in particular, what we're really doing is creating a so-called polarization current. Right? In this dielectric, what we're doing is we're creating this polarization current. So the polarization keeps flipping in this dielectric, and so there's this polarization current. And the question is, well, what happens, and how can I make this visible? This is the place where what Hertz did was actually very insightful. Actually, created a secondary circuit. Let's say that he did created a secondary circuit. This secondary circuit, but he left a little gap. And so, again, let me give you a minute or two to think about it. So in this scenario, okay, so what we're doing is we're introducing some polarization current in my dielectric, okay, or I'm introducing an alternating electric field. So what do we expect to happen in this secondary circuit? I'll give you a minute or two to think about this. Okay, anyone wanting to take a guess? So Jeffrey's saying oscillating voltage. You mean oscillating voltage in a secondary circuit? Okay. Now that is a good observation. But, what if I extrapolate this? What if I make the voltage high enough and this gap small enough? What do we expect to see? Sparks. Okay. Very good. Ionizing the air, and then if you make this voltage high enough, we expect to see sparks. But what is the kind of what is this? What is the kind of the physical mechanism behind this? Well, we can see it as follows. If voltage across D produces a polarization current or displacement current, then there will be an oscillating magnetic field, and this oscillating magnetic field will then give an electromotive force, okay, because the field is also coupled into the secondary current. So what we'd expect to see is an electromotive force across secondary circuit. Indeed, we hope to see sparks across the gap. This is actually one of the things that Hertz ended up showing even live in his lectures. And this is actually almost a direct demonstration that indeed, this polarization, this displacement current, and this alternating field produces something that behaves like an actual current, right? Because you create an oscillating magnetic field, which again is coupled into the secondary circuit, which then gives you an electromotive force. And again, we get these sparks. Now, what is actually quite remarkable is not exactly in this setup, but a setup that is very similar to this. He ended up, placing this here, some gap D. Okay. So he put some distance in between. Again, not exactly in this setup. A setup that looks fairly similar to this. He actually managed to introduce a gap, and still, even when he made the gap like a meter wide, he could show that there were still sparks going through the secondary circuit. And he even went as far as to walking in between the primary circuit and the secondary circuit, just walking in between. And still, there were sparks flying. Now they're different or similar circuits that he made in order to distill several properties, or at least induce several properties of this phenomenon. I'm not going to go through the entire series of experiments that he did, but for example, he also showed that there's some finite speed to this process, right? It's not something that happens instantaneously. And this is something that, the fact that there's some transmission, sorry, is that there's this induced current, which is like an actual current, that this happens at some finite, this process of the sparks happens at some finite speed, and C, that this happens over some distance. Still make this phenomena happen over some distance, and these really were the foundations that showed, you know, um, showed the existence of electromagnetic waves, and also, of course, the existence of this displacement current. And it's really these set of experiments that gave prominence to the notion of fields, field in magnetic fields, as opposed to, um, what maybe was there before, more fundamentally, like currents and forces, right? Because now you really do need the notion of these fields, and that one field could translate into another field, in order to get these wave phenomena, but that these wave phenomena are really there, right? You can walk in between, and the waves will still be transmitted. And there's no charges being transmitted or currents being transmitted. It really is the field that takes center stage. So let's take a look at how, in terms of the equations, this can be seen. So again, let's start with Maxwell's equations, time-dependent Maxwell's equations. By now, hopefully, you should be able to dream this, right? So if I wake you up at 3 a.m. in the morning, I shake you out of bed and say Maxwell's equations, you should be able to, without blinking, give me these equations. So again, remember, we in order to specify a field, we need a divergence and the curl. So the divergence of E is just rho over epsilon naught. Divergence of B, 0. And then curl of E equals to negative of the time derivative of B. And the curl of B equals to mu naught J plus the displacement current, or epsilon naught mu naught, and then the time derivative of the electric field. Okay. But we can actually combine these equations together, and what we'll see is that remarkably we end up with the concept of waves. So let's take a first step, and let's actually look at taking the curl of the curl of E. Now we can go back and think about the vector identities, or the vector operator identities, which basically states that the curl is just the divergence, is the gradient of the divergence minus the Laplacian. Okay, so this is an elementary vector, the differential vector operator result. Now, of course, the curl of E is given here is negative of the time derivative of B. So we can also write this as negative of the curl partial B partial T. Now here, of course, we note that the curl is just is a differential operator. Operator of spatial derivatives. of partial derivatives. And so we can interchange this with a partial derivative with respect to time. So we can change the order of this. And so we can write that this is partial t of the curl of B. But if you look above here, we actually have an expression for the curl of B. And I can equally put that in. So now I have the partial derivative with respect to time. And I put in this result over here. So this is just mu naught J plus epsilon naught mu naught partial E partial T. Okay, so we're getting, step by step, we're getting closer. We can, of course, also use substitution for this equation over here. Okay, so the divergence of E is simply given by rho over epsilon naught. So if I start on the other side, here, just put an equal sign here. I do apologize for the spaghetti writing, but I don't want to waste too many pages on this. So this is just rho over epsilon naught minus the Laplacian of E. Arrows everywhere. Okay, so now we can take a look at this here versus this here. And in particular, we can rearrange this altogether into the following equation. Arrange this into the following equation. We have the Laplacian of E minus epsilon naught mu naught partial E squared partial T squared equals to gradient of rho over epsilon naught plus mu naught partial J partial T. Okay. Now this here, especially if you take a look at the left versus the right-hand side, what we have here is a so-called wave equation. This is the Laplacian of E, and then the second time derivative of T, with respect to T, equals to some source term, right? The gradient of the charge density and also the time derivative of the current density. This is here so-called wave equation. Now, I'm not going to spend too much time discussing the wave equation in this lecture. We're going to probably take a look, or at least a more careful look, next lecture about the details of the wave equation. But for now, I just want to at least highlight that this here, what we have here is indeed a wave equation. Right? You should have seen wave equations also in string, right? String, a string with a particular tension also adheres to this so-called. On the right-hand side, of course, there's a source. Okay, now this is for the electric field. And to a certain extent, we hope to see some parity between the electric field and the magnetic field. The same as why, like for example, Maxwell came up with the so-called displacement current. So let's see if we can recover the same thing, but now for the magnetic field. So again, let me do this, and let's very basically start with the Maxwell's equations. I'm going to write these down until you can dream them. So the divergence of E, curl of E, and then the divergence of B, and then the curl of B. Like this. Okay? So Maxwell's equations in a time-dependent form. Now we take the same starting point and we take the curl of B. Again, is just the gradient of the divergence of B minus the Laplacian of B. Now, by virtue of this equation over here, note this as the negative of the Laplacian. But of course, the curl of B is given by this equation over here. So we can write down that this is the curl of mu naught J plus epsilon naught mu naught partial E. Now I can expand this into just the curl of J plus epsilon naught mu naught. And again, I'm just interchanging time derivative with the curl. And because the nabla is just a differential it's a differential derivative here, partial derivative. And I can interchange them with the partial derivative with respect to time. So write the curl in here, which again, using this equation here, I can simply turn this into a time derivative with respect to B. Here I've got mu naught, curl of J plus epsilon naught, mu naught, and this is simply now the second derivative. And here, it's a second derivative with respect to B. And again, I can rearrange this equation into the Laplacian of B minus epsilon naught mu naught partial B squared partial T squared equals minus mu naught curl of J. Okay, so again, we recover back a wave equation on the left-hand side, and then as a source term, which is now the curl of J. We recover the source term for the wave equation. So indeed, we show that the electric field and the magnetic field both satisfy the wave equation. This is a major step. Okay, now I want to go back into this set of equations that, had it not been for the introduction of the so-called displacement current, then I wouldn't be able to show that both the electric field and the magnetic field both satisfy the wave equation. And this is really where we had the hunch, because when we start off one of our first slides, that in this picture here, we want to have a magnetic field that would create an electric field, and then the electric field would then create a magnetic field. So this would be kind of something that ends up kind of being propagated. And so here is the actual mathematical form that basically now states, okay, indeed, we have a wave equation for the electric field and the magnetic field. Now, this is actually this is not, well, we can investigate this to a deeper level, right? Remember what we did in particular. You know, I hope you recall so-called Helmholtz theorem. So let me refresh your memory by recalling Helmholtz theorem. Which basically says that any field, any vector field, can be written as the negative gradient of some phi plus the curl of A. Okay? In this case, where phi is any scalar function, and A is any vector function. And the divergence of A is some specified function. Okay, so this is Helmholtz theorem. And the thing here is as follows, right? So I'll pose a problem and then we'll go for a quick break. But the potentials, time varying fields, know the following. We know that B equals to 0, right? The divergence of B equals to 0. So if it is purely solenoidal in this case, then I know that B can be written as the curl of some vector potential A. And this is something that, again, was also brought up by one of you in last lecture. The problem here is that the curl of E is no longer 0. As such, E is no longer the gradient of some scalar potential. And so, we, the question here is, how do we interpret the potentials in time varying fields? And so after the break, I want to discuss this problem here with you, and then also show kind of how in these time varying fields, how we can still write down equations for the potentials. Okay. Let's take a quick break, 5 minutes. So we'll come back at 3:40, and we're gonna discuss this aspect. Okay. Okay, welcome back. Let's continue this discussion. And in particular, the remaining part of this lecture, I want to show you the framework, how we can interpret the potentials when we look at time varying fields instead. So let's start our discussion with basically what we know from here is that we still have that the B field is solenoidal. So we know that the B field can be written as the curl of some vector potential. And now we know that E, the curl of E is no longer 0, and so we can no longer write E as a negative gradient of some phi. But we can do something similar. We can actually get something closer. And in particular, we know that the curl of E is the negative of the time derivative of B. But B, we know for sure, we can write as a vector potential. But here, what we have is the time derivative of the curl of A. Now again, I switch the order of these two. So here's the negative of the curl, the time derivative of A. But now we can define a field which is curlless. Right? Hopefully you can see it from this equation that I can now write the following. I can now write that the curl of not E, but E minus the time derivative of A equals to 0. Okay, I'm simply putting this, the right-hand side here, to the left-hand side, and I can take the curl out. And now I've got some field that then must equal to 0, some curlless field. So indeed, the field that has no curl is no longer E, but it's E minus the time derivative of A. And so it means that E minus partial A partial T equals to negative of some phi. And let me put a phi prime here. That is not to be confused with well, actually, that may cause even more confusion. Okay. But now this field instead is defined as the minus partial A partial T. Now that doesn't mean that this, of course, still means I can define E. But it's still negative of gradient of phi. But now with oops, no, a plus minus sign here. Okay. And this should be now minus partial A partial T. Okay, so indeed, what we have is time varying fields. Time varying fields is no longer just a negative of the gradient of phi, but there's also a time-dependent component of the vector potential. Okay, as I've alluded to, this actually gives you hints of special relativity, right? This mixing of the two things will actually give you some hints. But we'll get to that in the following lectures in the weeks. Okay, so this is an important result. Okay? No longer do we simply have a gradient for E, but now also a time-dependent component. Now remember where we, many lectures ago, we also ended up deriving a set of equations for the potentials. We remember the set of equations that govern the scalar potential and the vector potential. Anyone? Or, we're not looking at time-dependent fields. We're just looking at static fields. What are the what is the equation that covers the vector potential and the scalar? Anyone? Yeah, are you all frantically trying to derive it now, or just giving up? Again, just be reminded that rho over epsilon naught, and in the time-independent fields, 0 is as write it as a gradient of phi. And the equation above says that the gradient, the divergence of phi equals. Okay. So out here comes rolling the Laplace equation. Okay, but now we have a slightly different situation. We now have E that is no longer just the gradient, and so we don't expect to recover just the Laplace equation. Let's see what equation does come rolling out, and let's see how we can determine the potentials. Now, our first step is to just again start with Maxwell's equations. So whatever you do, there's always anything with electromagnetism, simply start with Maxwell's equation. So you will see me writing this down very often, also because I really want you to be beaten to death with this. Okay, this is something that you simply cannot forget anymore. Again, the Maxwell's equations are the following. Not partial t b. Okay? Where there's partial t underscore t, b is just partial b partial t. Okay, so now let's take a look and then how we can rewrite the potentials. Let's start with the divergence of E is rho over epsilon naught. But now I also know that the divergence of E is just the negative gradient phi, right? That's from this equation over here, negative the gradient of phi minus the time derivative of A. So I can shuffle things around now, where again I can now interchange the order of the divergence with the time derivative. So here I've got negative of the Laplacian minus time derivative of the gradient of A. And all of this equals to rho over epsilon naught. So if you will, I can now write Laplacian of phi equals minus rho over epsilon naught minus partial t of A. Sorry, divergence of A. Okay, but now I I can further rewrite this, and in particular, I can now have let's see, best way to okay. I can now add the I can now simply put in on both sides the epsilon naught mu naught partial oops, both sides partial phi partial t squared. Okay. I just put it in both sides. Maybe yeah, it's easier to even flip the sign. So I can simply write mu naught epsilon naught second partial derivative of phi with respect to t minus the Laplacian equals to space 9. So this is rho over epsilon naught plus. So I've got a time derivative of the divergence of A. Time derivative of the divergence of A plus, again, because I'm adding, oops, I'm adding this epsilon naught mu naught. Now I've got first time derivative of phi. Okay, so just going from the from this equation over here to this equation over here, I'm just on both sides adding a term that is epsilon naught mu naught second derivative of phi with respect to t. Okay, now it's a good moment to pause things here. Okay, what we do see on the left hand side is already the beginnings of the wave equation. Right? We've got a time derivative, and we've got the Laplacian. And then on the right hand side, we can see more or less a source term. Now, before I move on, I want to also take a few steps in looking at a similar equation that you would adopt for the vector potential. So similarly, I could evaluate the curl of B. I know to be curl of the curl of A, which is equals to, again, the gradient of the divergence of A minus the Laplacian of A. But we know that the curl of B is simply mu naught J plus epsilon naught mu naught partial E T. Okay, and so let's reorganize this to the Laplacian of A equals the gradient of the divergence of A then minus mu naught J minus mu naught epsilon naught partial E partial T. And again, here we can use the result that we've seen before, that the E can be written as the negative gradient of phi minus the time derivative of A. So we write this one down, partial A partial T, in such a way that now we can write gradient of the divergence of A minus mu naught J minus epsilon naught mu naught. Now the time derivative of the negative of the gradient of phi minus partial A partial T. And so again, we can flip all these terms around, and also the terms around in such a way that we can write epsilon naught mu naught second derivative of A minus the Laplacian of A, arrows everywhere, equals to mu naught J minus the gradient of the divergence of A plus epsilon naught mu naught partial phi partial T. Okay. So let me now give you a comparison of these two equations here. But this equation here at the bottom, where we've got on the left-hand side something that resembles the wave equation, right-hand side something that resembles the source term. Similarly here, got something that looks like a wave equation on the left-hand side, and then a source term on the right-hand side. But there's a problem. Okay? We've got this term over here, okay, which is the partial derivative of the divergence of A plus mu naught epsilon naught partial phi partial T. And here we've got the gradient of the divergence of A plus epsilon naught mu naught partial phi partial T. So if you look at here on both sides, our we don't really have a wave equation. We've got terms that depend on A. We've got terms that depend on phi. But there is something that then comes to the rescue. And that is would be a good time for a break. So why don't we just go all the way to the end? We do have something at hand which we can deploy. That is here. Okay? So this is going back a few slides. This is Helmholtz theorem. Helmholtz theorem says that any vector field can be written as the gradient or negative gradient of phi plus the curl of A. Phi is any scalar function, is any vector function. But the third thing that is important is this thing here. The divergence of A is some specified function. It only says that this whole system is fully determined if the divergence of A is some specified function. Just as some specified function. right? You don't have to actually, you can specify it any way you want. But only once you've specified it is your vector field completely determined. And I want to let this sink in, okay? Because this actually ends up being a very important aspect of classical electromagnetism. That's freedom to basically, or any field theory to be. That's the freedom to set the divergence of A. In order to fully specify the vector field in terms of a scalar function, scalar potential, and a vector potential. So we have this freedom here, and we note that this freedom is not spoiled. Sorry, this freedom is not spoiled by the time-dependent, formalism. Right, the equations are still the same. Our proof for all of this is still the same. And so we can indeed go back here and here, and we get to, at our will, give the divergence of A any form that we wish in order to fully specify the field. And so I'll give you a minute or two to relatively quickly see what is the best choice for the divergence of A. I'll give you 2 minutes. Anyone want to take a crack at this? What would be a good choice for the divergence of A? Zero or so Liu Ling is 0 or minus mu naught epsilon naught partial t pi. Harry says tempted to say 0. So again, before we saw that, right? 0 is a good choice where we or is one of the choices. It's a good choice, in, let's say, time independent fields. That's fine. But indeed here, take a look at these two equations over here. Actually have this this factor here. Okay. This factor here, this factor here. And on both sides, if this term were to disappear, it would drastically simplify our equations. And so indeed, you know, is that Helmholtz theorem going to provides freedom to pick gradient divergence of A, or to choose gradient of A. And a particular choice in this case is to say that the divergence plus mu naught epsilon naught partial phi partial t equals 0. Why? Because the equation that we end up with, now this term here equals 0. And so we end up with this term here. And for this equation, we end up with these three terms here. Just write them down. We got epsilon naught mu naught partial phi squared partial t squared minus the Laplacian of phi equals rho over epsilon naught. And got that other equation again is epsilon naught mu naught partial a squared partial t squared minus Laplacian of a squared equals mu naught. Okay. Here, two wave equations. So by selecting a particular form for the divergence of A, again, we call that a gauge. And in this case, this is actually called the so-called Lorentz gauge. We end up also with two wave equations for the potentials. Okay. Now, again, this is under, in particular, the Lorentz gauge. You can see now that the potentials also satisfy the wave equation. And so we end up with, we end up with the electromagnetism, Maxwell's equations, being able to write it as follows. So if we introduce so-called D'Alembertian operator, which is that what is a box 1 over c squared, okay, where c is just a constant for now. We'll discuss this constant in detail next lecture. Okay. Where it's just the some constant times the second partial derivative with respect to time minus the Laplacian. So this is an operator, and so Maxwell's equations summarized as the box operator on E equals to the gradient of the charge density plus mu naught time derivative of current density of the box operator, the D'Alembertian on B, just minus mu naught the curl of J. This, of course, can also be written in terms of the potentials of box phi equals rho over epsilon naught. The box A equals mu naught J. Of course, this here is contingent upon the divergence of A being equal to minus epsilon naught mu naught partial phi partial t. Okay. So indeed, we now arrived at just using Maxwell's equations, right? Because again, recall that we simply started with Maxwell's equations. Set here, and this set here, where we simply put in the set of Maxwell's equations. We're starting here, and then we just put in another Maxwell's equation over here, and then we put one of Maxwell's equations in here, and then when we have B, we put in this expression for B in there as well. And so we basically one by one slot in Maxwell's equations, and we simply end up with this set, which is more or less a summary of Maxwell's equations. Okay. And this here, this box operator, we'll study that in detail next lecture, and show that this indeed comes, or it becomes, this is a wave operator. And so the solutions to this equation are indeed wave solutions. Okay. Now, I want to just close out again by teasing something here. Of course, when we, as I was already saying, that there are hints of relativity here. That is that for one, this here is a constant, okay, 1 over c squared. If you actually take a look at, if I want to write this as box E or box B, and I compare it to this equation over here, sorry, this, where did I put it? Okay, so here is indeed this 1 over c squared. Similarly here, this is the 1 over c squared. So we end up with, make the identification that c squared equals 1 over mu naught epsilon naught, right? Because epsilon naught and mu naught are simply constants. Right? Go all the way back to our one of the first lectures. Epsilon naught and mu naught are simply experimentally determined constants. Well, c is a constant, and this is remarkable. Right? This equation is only governed by one constant. And so irrespective, this is the key, irrespective of what velocity you would be traveling, this equation doesn't change, right? There's nowhere in this equation that gives you a sense of a reference frame. This equation should hold for any observer. And the c squared here, or the c squared equals 1 over epsilon of mu naught, it's the same for everyone. And we'll see, next week, probably sometime, if time permits, I'll discuss it in more detail. This basically means that the c, which ends up being the speed of light, is universal. It doesn't change with the observer. This is already kind of amongst the first hints of relativity here. Also, if you take a look at this set of equations, very key, very pivotal that, you know, concept of relativity is that space and time are actually combined into a concept called space-time. Combine space and time. I'll get to your question. So, combine the concept of space and time. What you end up doing is combining a scalar, time, with a vector. You can actually see that, equivalently, I could combine these two, combine the vector potential and the scalar potential, and I can combine them, and I still have a valid equation. Okay? Let's make these two set of equations one single equation. And so it also comes out, not just through the C, it also comes out by combining this, that there's a very natural way that, relativistic effects or relativity is actually already embedded into this set of equations. I can just by simply combining these two. It comes out just purely through, just a set of equations and a set of experiments that we arrived at a theory which is inherently already fits with special relativity. So as I was saying, there are hints, there are clues in here that already point to relativity. Okay, this is more or less what I wanted to say for today. I'll take some questions now, and I'll start with the question that was posted here on the chat. And so Ku Che Xuan, if I pronounce it correctly. What if we choose the divergence of A, that the summation be equal to a constant? I understand what you mean. So let's take this. Let's take this equation here. So if you're saying that you let divergence of A equal to the summation, which summation are you talking about? Are you talking about this summation? The one in the time derivative. Okay, so you're saying that if I make this to be a constant instead, right? Okay, instead of 0. Let's see. I mean, firstly, yes, the equations will not be different because in this case, this drops out, right? This is make this the inside here to be a constant. Then for both equations, so here, this would drop, and yeah, that does not seem to have much ramification. I mean, it's the first time I've heard it asked like this. I may need to think about it a little bit more carefully. But at first glance, it doesn't seem to cause major problems. Of course, the question is, well, what would that constant be? And the other thing that makes this a little bit more difficult, and more difficult than needs be, is of course, in order to construct this, if you say that equals to a constant, you end up just needing to basically to solve a more difficult set of equations, and you're not gaining much. But I really want to stress that this is, this is a choice. Okay, so yes, you are free to choose this to be a constant. The question is just, why would you choose a different constant than 0? That is not necessarily useful, especially if you need to evolve things in this way. But sure, you're free to. There's nothing preventing you from doing that. Alex is asking, have I drafted the finals yet? So it's not on paper yet, but I more or less know what I'm going to ask you. So yes, I more or less know. I would one hint I don't mind dropping is that it's expect something of the level of the midterm, very comparable to the midterm, uh, but now just introducing more new concepts. That is the matter part, and then you will get you'll get a question about time varying fields as well. So yeah, so it's not going to be more difficult than the midterm in the sense that you will need to make sure you can introduce the concept of dielectric materials and magnetic materials into questions that are very similar of level to the midterm. So I would firstly suggest you make sure you really study also the midterm. That's important. And I've also this week's problem set. For those who have noticed it, there were some typos in there, so I actually had to replace it. There's a version 2 that's uploaded. I would say, because we really built up the difficulty level in terms of the problem sets for the dielectric materials, and this last set, this last problem set is again, I wouldn't say killer, but it's something that I think really sums up kind of the full richness of what we've done so far. Right, we've looked at how to solve the Poisson and Laplace equations, and we how to deal with boundary conditions and other aspects related to dielectric material. So another part that I think is important to study is really how to combine all of these features, and so I've taken feedback that you guys have provided for me also, that it's maybe better to have problem sets that kind of increase in complexity so that you're prepared for the final. Okay, so that's that. Next time, will there also be 2 questions only, or the questions will be more discretized? Of course, the final is going to be longer than the midterm, so there'll be more questions. Um, Again, the final have not been made, so I can't say too much about it. But it's still, I mean, you are expected to be able to kind of know the steps you need to undertake. Right? I'm not going to spell out every single step, guiding you through the entire question where you just have to fill in some numbers. There has to be some challenge as well. But as most of you have seen, also the midterm, very reasonable, the scores that all of you had made. So I just say that there's a projected grade there as well. The midterm is something that you should be aiming towards in terms of difficulty. There's one more thing I want to bring up. Maybe I should have brought it up in the earlier part. I've seen that quite a few of you have signed up for 4460 relativity. I appreciate it. I also know that some people are having difficulty sign up because the course is now oversubscribed. We've reached the limit, but I'm going to be talking to the general office to see if I can expand the number of slots, so that if you guys want to take 4460 next term, then there should be space. I appreciate it. I've seen in the registration already that quite a few of you from the third year who are now doing this course have also signed up for relativity. I'll try to bridge, in the last year, try to as much as possible bridge and take a step towards special relativity, the transition fun way. Okay. Any questions about this lecture? Okay. See any hands up? Let me stop the recording.